When we look at the introduction to this paper, we say we in a real world where data analytics has become a problem. A huge amount of data are collected from multiple sources without label information, which is often with different types, structures, and distributions. We can call this heterogeneous data. An example is sentiment analysis tasks. The data may contain text, images, and videos from Twitter, Facebook, and YouTube. To actually extract knowledge from such big and label heterogeneous data, advanced unsupervised learning techniques are required to actually have a large model capacity or complexity. Secondly, to have the ability to integrate information from multiple sources, and perhaps the last one is to have a high learning speed. Many researchers have enhanced model capacity by combining unsupervised learning with deep learning to propose deep unsupervised learning models. These models inherit the powerful model capacity from deep neural networks that can reveal highly complex patterns and extremely nonlinear relations. But however, most of them fail to learn from multiple sources. They are challenged by types, relations, and distributions of the heterogeneous data because of the deep neural networks they actually employ. Without strong supervised information, the deep neural networks may arbitrarily fit complex heterogeneous data that leads to meaningless solutions. One promising way to reveal information from multiple sources is using the multiple learning kernel. First adopts multiple kernels to capture heterogeneous data characteristics from different sources. That's brief of the introduction. When we look at the problem statement here, we say more recently, unsupervised MKLs has been studied to tackle the heterogeneous data learning without supervised labels. Unsupervised MKL uses multiple kernels to distribute information from various sources. Although the unsupervised multiple kernel learning achieves remarkable performance in unsupervised heterogeneous data learning, most of the current unsupervised MKL methods are with a slow learning speed. The slow learning speed is mainly caused by the iterative numerical solution, which is adopted by these methods for optimizing the kernel combination coefficients. It does not satisfy the requirements of handling a large amount of data and real-time learning. So to address these issues, a fast unsupervised heterogeneous data learning approach, we can call it two-stage unsupervised multiple kernel extreme learning machine, is proposed. TUML iteratively extracts information from multiple sources and learns the heterogeneous data representation with closed form solutions. It adopts multiple kernels to capture information in heterogeneous data and learns an optimal kernel for heterogeneous data representation. Methodology. The project or the paper employed several methodologies. One is a novel unsupervised learning method from multiple sources. The proposed method here provides an effective and efficient way to analyze multiple sources in an supervised fashion. It breaks out the obstacle of low learning speed for high performance big data analytics. Another methodology is the fast unsupervised multiple kernel learning method. The proposed method here is the fast unsupervised multiple kernel learning method. It shows a promising paradigm for the multiple kernel learning community to efficiently handle large-scale unlabeled data. Lastly, the project employed another methodology called the proposed method proves it is with a low time complexity and can be converted within finite steps. The theoretical evidence guarantees the high learning speed of the proposed method in real large-scale multiple sources learning applications. What are the key contributions of this project? The paper presents a comprehensive experiment on 13 real-life datasets. The Haberman, Biodec, Seeds, Wine, Irish, Glass, Image Segment, Libra's Movement, Frogs, Wine Quality, Studlock, Isolate, and Shovel to evaluate the proposed TUML method. The proposed TUML can efficiently learn from multiple sources, which is up to 140,000 times faster compared to the state-of-the-art method. This same proposed method captures well the local and global relations of objects, producing results substantially better than previous unsupervised multiple kernel learning methods, up to 9.71% in terms of accuracy, 12.6% in terms of NMI, and 15% in terms of the purity. The proposed method converges very fast within 2 or 3 iterations. Okay, the proposed method also is quite stable regarding its key parameters. So with this above evidence, the proposed method is fit for the first unsupervised learning from multiple sources, and it can be adopted in other unsupervised big data analytics scenarios that enable better performance. What are the challenges in the heterogeneous data? Heterogeneous data learning faces several challenges in real application. These challenges may include, but may not be limited to, high dimension, complex relations, multiple structures, heterogeneous distributions, large number of objects, and lacking supervised information. Many efforts are being made on handling complex dimensional heterogeneous distributed data. An example is using the kernel methods. However, the challenges brought by a large number of objects and of lacking supervised information are not well analyzed and solved. Related works. This work is related to about 2 learning paradigms. One is the unsupervised deep learning that utilizes deep models to handle large data complex. The other is unsupervised multiple view learning that leverages heterogeneous information from multiple views or models. When we look at the unsupervised deep learning, we say recently lots of effort have been done for unsupervised deep learning, which aims to reveal complex relations, patterns, knowledge in huge amount of data. Typically, the unsupervised deep learning method combines an unsupervised objective and deep neural networks to learn a powerful data representation. When it comes to the unsupervised multiple view learning, this unsupervised multiple view learning aims to learn heterogeneous data without supervised information. As amongst the various unsupervised multiple view learning methods, we have the unsupervised multiple kernel learning methods, which attracts the most attention because of the ability to represent data The theoretical analysis of the Thom-Elm properties. We say here that the theoretical analysis will first analyze the time complexity of the Thom-Elm and then discuss its convergence properties. With the time complexity analysis, the time complexity of Thom-Elm is determined by the k-space construction, the optimal kernel learning, and the number of iterations. For the k-space construction, the main cost is from the kernel k-means clustering, and the optimal kernel learning has its time cost determined by the constructing k-space. Convergence analysis. The convergence analysis of the two-stage unsupervised multiple kernel learning machine algorithm is guaranteed by the convergence to a local optimal in some finite steps. The experiments carried out in the projects focused on comparing the two-stage unsupervised multiple kernel extreme learning machine to several state-of-the-art heterogeneous data learning methods to evaluate Thom-Elm performance in terms of both learning and learning speed. Okay, the experimental results support the theoretical analysis that Thom-Elm extremely improves the learning speed while achieving the better or compatible clustering accuracy compared with current multiple kernel clustering methods. When we look at the benchmark data sets employed in the experiment, this data used included the Haberman, Biodex, seeds, wine, iris, glass, image segment, Libra's movement, frogs, wine quality, stud log, isolate, and shuttle. These data sets can be accessed from the UCI machine learning repository. We look at the summary of these data sets here based on the number of instances, the number of attributes, and the number of classes. The testing of this algorithm is enabled by the information retrieval performance. Okay, which is a task that heavily depends on data representation. This performance reflects whether this algorithm can well integrate the heterogeneous information from multiple sources. We look at 4 data sources here. The iris, glass, seeds, and wine are tested for Thom-Elm enabled retrieval performance. We say the precision at k. The k is and the recall at k of retrieval are used as evaluation metrics. So we say with accurate metrics or with supervised metrics, we get some accurate clustering. So we say accuracy of unsupervised clustering algorithm is best described in this table using the highlighted bold faces. We can see them here. So when we continue with the testing and testing Thom-Elm clustering effectiveness, we look at the evaluation in terms of accuracy, NMI, and purity. The results indicates that the clustering effectiveness is comparable with its competitors. We have around 3 tables here. One table which is based on accuracy, the other table of NMI of the unsupervised clustering, and the third table here is of purity and clustering. Just because of time, I'll highlight and rush over this. Algorithm employed in this project, we say this project employed the k-means algorithm as unsupervised learning to learn the optimal kernel combination coefficients, and also employed a fast unsupervised heterogeneous data learning algorithm, which we call it a 2-stage unsupervised multiple kernel extreme learning machine, to alternatively extract information from multiple sources and learns the heterogeneous data representation with closed form solution, which enables it is extremely fast speed. Conclusions in this work: this paper proposed a 2-stage unsupervised multiple kernel extreme learning machine, which is more flexible algorithm for fast and supervised heterogeneous data learning. So according to the experiments carried, the learning speed can achieve as much as 1,000 times faster than RMKKM, which is 140,000 times faster than LMKKM, and also 8,500 times faster than the MKC or the LCAM. Meanwhile, the clustering accuracy of the proposed algorithm is comparable with its competitors as seen previously in the tables. Experimental results clearly demonstrate that superiority of this algorithm is so high. So in the future, when we what the works focus on, it should consider how to adaptively adjust the base kernels to fit the dynamic heterogeneous data distribution to be considered. I thank you for listening.